Hello, my friend, and welcome to Orbital Dreams. There are some mysteries so close to us that we forget they are mysteries at all. Water is one of them. It moves through your body, gathers in clouds, softens the ground, cools the air, and fills most of the living world. Yet this simple liquid has a strange shape, a hidden molecular network, a surface that behaves like a delicate skin, and a frozen form that floats when it seems like it should sink. And even after centuries of studying it, water still has strange edges. It can remain liquid below its freezing point. It can take on hidden forms under pressure. It can behave differently in tiny spaces than it does in open air. The more closely science looks, the more water seems less like a background substance and more like one of nature's quiet puzzles. So tonight we'll gently explore why water is much stranger than it appears, and why this ordinary substance may be one of the reasons Earth became a living world. And if you came here with a busy mind, stress from the day, or that restless feeling that makes sleep feel far away, you are welcome here. You do not have to focus hard. You do not have to remember everything. Just let the story of water move slowly around you, like a calm river carrying the weight of the day downstream. Get comfortable, my friend. Let your breathing slow, and let's begin. Chapter 1. The most familiar mystery on Earth. To understand water is to understand one of the quiet foundations of life: climate, chemistry, and perhaps even the search for life beyond Earth. Water is so familiar that it almost disappears from our attention. It waits in a glass beside the bed. It runs from the tap with a sound we recognize before we think about it. It gathers on windows, falls from clouds, rises from kettles, softens soil, fills the sea, moves through blood, and rests inside every living cell. We meet it so often that we can begin to mistake familiarity for simplicity. But water is not simple. It is one of the strangest ordinary substances on Earth. At first glance, water seems like the most basic material imaginable. It is clear, quiet, and easy to overlook. It has no strong color in a cup. It does not hold a shape of its own. It slips through fingers, follows gravity, spreads into puddles, and takes the form of whatever contains it. Yet beneath that calm appearance is a substance whose behavior is unusual in ways that matter deeply. If water were only slightly different, the world around us would be almost unrecognizable. The strangeness begins at a scale far too small to see. Each water molecule is built from 2 hydrogen atoms joined to 1 oxygen atom. That may sound simple, but the arrangement is not a straight line. The molecule has a bent shape, and because oxygen pulls more strongly on shared electrons than hydrogen does, the molecule has an uneven distribution of electric charge. One side is slightly negative, while the hydrogen side is slightly positive. This makes water polar, which means each tiny molecule behaves a little like a microscopic object with 2 different electrical sides. This small imbalance changes almost everything. Water molecules are attracted to one another in a special way. The slightly positive hydrogen side of one molecule can be drawn toward the slightly negative oxygen side of another. These attractions are called hydrogen bonds. They are weaker than the bonds holding the atoms inside each molecule together, but they are strong enough to give water a hidden structure. Liquid water is not a random crowd of separate molecules drifting alone. It is more like a restless network, constantly forming, breaking, and forming again. This invisible network is why water feels so ordinary and yet behaves so unusually. It helps explain why water clings to itself. It helps explain why droplets bead up on leaves and windows. It helps explain why a small insect can stand on a pond surface without immediately sinking. The surface of water behaves as though it has a delicate skin, because the molecules at the surface are pulled inward and sideways by their neighbors. This skin is not solid, but it is real enough to shape rain, bubbles, ripples, and foam. The same molecular attraction also gives water an unusual relationship with heat. Many liquids warm quickly and cool quickly. Water resists sudden change. It takes a great deal of energy to raise its temperature, because much of that energy goes into disturbing the hydrogen bond network before the molecules can move faster. This is one reason oceans moderate the climate of Earth. The sea absorbs, stores, and releases heat slowly, softening temperature extremes across the planet. Coastal places often feel different from inland places because vast amounts of water are quietly buffering the air. This property also matters inside the body. Living organisms are full of water, and because water changes temperature slowly, it helps protect living systems from rapid thermal swings. When you sweat, water carries heat away as it evaporates. When blood moves through the body, water helps transport warmth, dissolved substances, and chemical signals. Life uses water not simply as a background fluid, but as a working environment. The chemistry of cells takes place in water, because water allows many substances to dissolve, meet, separate, and react. This dissolving power is another part of its mystery. Water is sometimes called a universal solvent, though it does not dissolve everything. Oil, wax, and many nonpolar substances resist it, but water is exceptionally good at surrounding charged particles and polar molecules. Salt crystals can break apart in water because water molecules gather around the separated charged pieces, stabilizing them and carrying them through the liquid. Minerals, nutrients, gases, and biological molecules can move through water in ways that make rivers, oceans, soil, and cells chemically alive. A river is not just water flowing downhill. It is water carrying pieces of the world with it. It dissolves minerals from rock. It transports clay, organic matter, and salts. It reshapes valleys and feeds ecosystems. Ocean water is not just a large volume of liquid. It is a chemical memory of the planet, holding dissolved ions, gases, heat, and traces of countless processes occurring on land, in the atmosphere, and along the seafloor. Even when water looks empty, it is often carrying a quiet record of where it has been. Then there is ice, perhaps water's most famous oddity. Most substances become denser as they freeze. Their molecules slow down and pack more tightly together. Water does something different. As it freezes, its molecules arrange into an open crystal structure shaped by hydrogen bonding. This structure takes up more space than liquid water, making ice less dense than the liquid below it. That is why ice floats. This simple fact has enormous consequences. If ice sank, lakes and oceans in cold climates could freeze from the bottom upward. Instead, ice forms a floating layer on top, where it can insulate the liquid water underneath. Aquatic life can survive beneath winter ice because water's frozen form rises rather than disappears into the depths. A strange molecular detail becomes a planetary protection system. Water also becomes most dense as a liquid before it freezes, then expands as it turns to ice. This is why freezing water can crack stone, burst pipes, and slowly widen tiny openings in rock. The gentle liquid that smooths pebbles in a stream can become a powerful force when temperatures fall. It can shape mountains grain by grain and season by season. The same substance that nourishes life can fracture landscapes through patient pressure. Water's familiarity hides its role as a boundary between worlds. It connects the atmosphere to the ground through rain and evaporation. It connects the surface to the depths through rivers, glaciers, aquifers, and oceans. It connects living bodies to their surroundings through thirst, breath, food, and waste. It moves through cycles so old and continuous that every glass of water feels both ordinary and ancient. Some of the molecules in that glass may have passed through clouds, seas, ice, plants, animals, and stone across deep stretches of time. This does not mean individual water molecules remember in any mystical sense. They do not carry thoughts or intentions. But water participates in cycles that link many parts of Earth together. A molecule can evaporate from the ocean, become part of a cloud, fall as rain, seep through soil, enter a plant, return to the air, freeze into snow, or drift through a river toward the sea. Water is always changing location and state, yet the larger cycle continues with quiet persistence. That cycle is powered by sunlight, gravity, and the physical properties of water itself. Sunlight warms oceans and lakes, allowing water to evaporate. Rising air cools and vapor condenses into clouds. Droplets grow, fall, and return to the surface as rain or snow. Gravity pulls water through rivers and underground channels. Heat moves it upward again. The result is a planetary circulation system that refreshes landscapes, feeds ecosystems, and helps regulate climate. The more carefully we look at water, the less it feels like a passive substance. It is active in nearly every system that makes Earth recognizable. It shapes weather, it carves canyons, it transports nutrients, it stores heat, it controls the texture of clouds. It softens food, carries sound, dissolves minerals, forms crystals, and creates habitats from mountain streams to deep oceans. It is simple enough for a child to splash in, and complex enough that scientists still study its behavior in detail. That combination is what makes water such a powerful subject. It is both intimate and cosmic. It is in the cup beside you, but it is also in comets, icy moons, interstellar clouds, and distant planetary systems. When scientists search for life elsewhere, they often begin by asking whether liquid water could exist there. This is not because water is magical. It is because life as we know it depends on chemistry that water makes possible. Where there is water, there may be movement, exchange, dissolving, transport, and reaction. There may be a place where complexity can begin, and here on Earth that complexity has already happened. Water helped create the conditions in which life could emerge and continue. It became the medium inside cells, the fluid of oceans, the breath of clouds, and the hidden thread joining climate, geology, and biology. Every living thing carries some part of this story. Even the human body is not separate from water's planetary journey. We are, in a quiet sense, temporary arrangements of matter through which water passes. So the next time water runs over your hands or gathers in a glass or taps softly against a window, it may be worth noticing it with fresh attention. This clear liquid is not merely background, it is one of the reasons the Earth feels alive. It is one of the reasons weather moves, forests grow, cells function, and oceans breathe heat into the air. For tonight, you do not have to solve its mystery. You can simply let the thought of water become gentle and steady. Imagine its slow movement through rivers, clouds, and quiet seas, carrying the day away one ripple at a time. Let your breathing soften, let your thoughts settle, and allow this familiar mystery to become a calm place to rest. Chapter 2. The strange shape of a water molecule. The mystery of water begins with a shape so small that no eye can see it. Yet that shape quietly influences oceans, clouds, ice, rain, and the chemistry of life. A single water molecule is tiny beyond ordinary imagination. If you could shrink down far enough to meet one, it would not look like the smooth liquid we know from a glass or a river. It would be a small arrangement of atoms, with one oxygen atom joined to two hydrogen atoms. Those words sound almost too simple. One oxygen, two hydrogens, and from that modest structure comes a substance that can carve valleys, carry heat across the planet, fill living cells, fall from the sky, and gather as snow on mountains. The first surprise is that a water molecule is not straight. The two hydrogen atoms do not sit on opposite sides of the oxygen like beads on a line. They are arranged at an angle, giving the molecule a bent shape. Many drawings show it almost like a tiny open pair of arms, with oxygen at the center and hydrogen atoms reaching outward. This bend is one of the quiet reasons water behaves the way it does. If the molecule were straight, some of water's most important properties would be very different. To understand why water bends, we have to think about electrons. Atoms are held together through the behavior of electrons around them. In water, the oxygen atom shares electrons with each hydrogen atom. These shared electrons help form chemical bonds, holding the atoms together as one molecule. But oxygen also has electrons that are not shared with hydrogen. These are often called lone pairs. They belong to the oxygen's outer region and take up space around it. Electrons are tiny, but they matter enormously because regions of electron density repel one another. Around the oxygen atom, the shared bonding regions and the lone pair regions arrange themselves in a way that reduces crowding. The result is a three-dimensional arrangement that places the two hydrogen atoms at an angle rather than in a straight line. The lone pairs push more strongly than the bonding regions, so the angle between the hydrogens is squeezed slightly inward. What we see as a bent molecule is really the visible part of a deeper electronic arrangement. This is an important idea because the shape of a molecule is not decided by atoms alone. It is also decided by where the electrons are most likely to be. Chemistry is often a story of invisible geometry. The atoms are the points we can name, but the electrons help determine the architecture. In water, that architecture is small, stable, and deeply consequential. The second surprise is that the bonds inside water are uneven. Oxygen and hydrogen do not share electrons equally. Oxygen has a stronger pull on the shared electrons, so the electrons spend more time closer to oxygen than to hydrogen. This does not make the whole molecule charged. A water molecule remains electrically neutral overall, but the charge is distributed unevenly. The oxygen side becomes slightly negative, while the hydrogen side becomes slightly positive. This unevenness gives the molecule polarity. A polar molecule has different electrical character on different sides. You can imagine it as a tiny object with a gentle imbalance built into it. One end is a little more negative, and another region is a little more positive. In water, the bent shape makes this imbalance especially important. Because the molecule is bent, the poles of the two bonds do not cancel each other out. They combine into a single overall polarity. If the molecule were straight, the electrical poles could point in opposite directions and partly cancel. But because water is bent, the molecule has a clear positive side near the hydrogens and a clear negative side near the oxygen. This is one of those details that seems minor until you realize how much depends on it. A small change in shape changes the entire personality of the substance. Polarity is why water molecules notice each other. The slightly positive hydrogen side of one molecule is attracted to the slightly negative oxygen side of another. These attractions are known as hydrogen bonds. They are different from the strong bonds inside the molecule itself. The bond holding hydrogen to oxygen is a covalent bond where electrons are shared. A hydrogen bond is a weaker attraction between neighboring molecules. Yet in large numbers, these weaker attractions become powerful. This gives liquid water a restless inner social life. Molecules are always moving, rotating, approaching, separating, and reconnecting. Hydrogen bonds form and break extremely quickly. No single arrangement lasts very long in ordinary liquid water, but the tendency to connect is always there. The liquid is therefore a shifting network, constantly rearranging itself while staying fluid. This picture helps explain why the molecular shape matters so much. The bent form gives each molecule directions of attraction. The oxygen side can attract hydrogens from other molecules. The hydrogen side can point toward oxygen atoms nearby. Water molecules are therefore not like smooth, featureless balls bouncing randomly. They have orientation. They turn toward one another in preferred ways. Their shape gives the liquid a hidden order, even while it remains fluid. This hidden order is one reason water is so good at interacting with other substances. Charged particles, polar molecules, and many biological compounds can be surrounded by water molecules in organized ways. The oxygen sides may face positive regions, while the hydrogen sides may face negative regions. Water can arrange itself around dissolved materials, helping separate them and keep them moving through the liquid. This is essential in oceans, soils, and living cells. Inside a cell, water is much more than empty space between larger molecules. It surrounds proteins, salts, sugars, genetic material, and countless other substances. Its polarity helps create the environment in which biological chemistry can happen. Proteins fold partly because some parts of them interact well with water, while other parts avoid it. Cell membranes form partly because fatty molecules respond to water's polarity in a special way. The shape of a water molecule reaches outward into the architecture of life. The bent shape also helps explain why water feels so different from many other small molecules. Molecules of similar size can be gases at ordinary temperatures. Water, however, is liquid across much of Earth's surface because its molecules attract each other strongly enough to stay close together. Those attractions arise from polarity and hydrogen bonding, both of which trace back to molecular shape and electron distribution. The molecule is small, but it does not behave as if it wants to drift away easily. This is why water can seem gentle and strong at the same time. It pours softly, but its molecules cling together more than their size might suggest. A drop can hold a rounded form because molecules at its surface pull inward on one another. A thin film of water can rise slightly in a narrow tube because water molecules are attracted both to each other and to certain surfaces. These are visible consequences of invisible attraction. What looks like a simple drop is actually a crowd of polar molecules coordinating their motion through countless small pulls. There is another quiet lesson here. The properties of water are connected directly to its structure. The angle, the electron distribution, the polarity, and the attractions between molecules all belong to the same story. Shape becomes interaction. Interaction becomes liquid behavior. Liquid behavior becomes weather, biology, geology, and climate. When we say water is strange, we do not mean it breaks the rules of nature. Water follows the rules very carefully. Its strangeness comes from how much those rules produce from such a small design. A bent molecule, a strong oxygen pull on electrons, 2 hydrogen atoms, and 2 lone electron pairs are enough to create a substance with unusual power. The simplicity is part of the wonder. Water does not need a complicated molecule to become complicated in the world. The more closely we look, the more the ordinary surface disappears. A glass of water is a vast collection of bent polar molecules, each one surrounded by others, each one responding to electric attractions, each one helping create the shared behavior we experience as wetness, flow, dissolving, cooling, and life. The liquid has no visible machinery, yet it is full of motion and structure at the molecular scale. This also changes how we think about the natural world. So much of reality depends on shapes we never see. The softness of rain, the hardness of ice, the curve of a droplet, the chemistry of blood, and the survival of a cell all depend on invisible arrangements of atoms and electrons. The familiar world is built from hidden geometry. Water is one of the clearest examples because its small shape leaves such large fingerprints everywhere. So when water rests in your hand or gathers on a window, it is carrying an unseen architecture. The molecule is bent, polar, and alive with attraction in a physical sense. It is not alive as an organism is alive, but it is active, responsive, and deeply connected to the conditions that make life possible. Its shape is a quiet instruction written into matter, telling molecules how to meet, how to turn, how to gather, and how to move. And perhaps that is the most beautiful part of water's strange shape. It reminds us that the world does not need to look mysterious in order to be mysterious. Sometimes the deepest wonders are the ones that have been beside us all along, clear enough to see through, gentle enough to drink, and intricate enough to shape a planet. For now, let that thought become light and easy. Somewhere, water is moving through clouds, resting in dark soil, drifting through rivers, and gathering silently in the sea. You can let the day loosen a little, breathe slowly, and rest with the quiet knowledge that even the simplest things around you are held together by hidden patterns. Chapter 3. Hydrogen bonds, the invisible network inside water. Inside every quiet glass of water, there is a restless invisible network, forming and breaking so quickly that the liquid seems simple only because our senses are too slow to follow it. To the eye, water looks continuous. It seems like one smooth substance with no visible seams and no internal architecture. When you pour it, it bends around the rim of a glass. When it rests, it settles into a level surface. When it falls as rain, it separates into droplets. But at the molecular scale, water is a crowded world of movement. Each molecule is surrounded by others, and each one is constantly being pulled, nudged, rotated, and released by tiny attractions. The most important of these attractions is the hydrogen bond. It is one of the main reasons water behaves so differently from many other small molecules. A hydrogen bond forms because water molecules are polar. The oxygen side of a water molecule carries a slight negative character, while the hydrogen side carries a slight positive character. When the hydrogen side of one molecule comes close to the oxygen side of another, the two can attract each other. This attraction is weaker than the chemical bond inside the molecule, yet stronger and more directional than a casual molecular pull. That difference matters. The hydrogen atoms are firmly attached to their own oxygen atom by strong covalent bonds. Those bonds make the water molecule itself. Hydrogen bonds, by contrast, are attractions between neighboring water molecules. They do not fuse the molecules into one larger molecule. They guide how nearby molecules approach, turn, linger, and separate. In liquid water, this guidance happens everywhere at once. A single water molecule can take part in several hydrogen bonds. Its two hydrogen atoms can point toward oxygen atoms on neighboring molecules, allowing it to act as a hydrogen bond donor. Its oxygen atom has electron-rich regions that can accept hydrogen bonds from nearby hydrogens. In a nearly ideal arrangement, a water molecule can connect with up to 4 neighbors. The preferred geometry is roughly tetrahedral, meaning the connections tend to spread out in 3 dimensions rather than lie flat in a simple plane. Liquid water does not keep this ideal arrangement perfectly. At ordinary temperatures, the molecules are moving too quickly for a frozen pattern to last. Some hydrogen bonds are stretched, some are bent, some are broken. Some molecules have fewer partners for a moment, while others form new ones almost immediately. The network is therefore both ordered and disordered. It has preferred directions, but it never stops rearranging. This is the heart of the mystery. Water is liquid because its molecules can move past one another. Yet it is an unusual liquid because they do not move as completely independent particles. They remain loosely connected through a temporary network. Imagine a crowd in which everyone is walking, turning, and changing places, while brief handshakes appear and disappear between them. The crowd has no fixed shape, yet the handshakes still influence how everyone moves. Water is more subtle than that image, but the idea helps reveal why a liquid can have hidden structure. These hydrogen bonds last for extremely short periods. On molecular timescales, they can appear and disappear in trillionths of a second. To us, that is unimaginably fast. To water, it is part of ordinary life. The liquid is constantly renewing itself. There is no single permanent network inside a glass of water. There is a pattern of making and unmaking, a continuous exchange of partners that gives water both flexibility and cohesion. Because the bonds are temporary, water can flow. Because they are numerous, water resists being pulled apart. This balance gives water its familiar character. It pours easily, yet droplets hold together. It spreads across surfaces, yet can gather into beads. It moves through soil and vessels, yet remains cohesive enough to pull itself along narrow spaces. Many later properties of water grow from this balance between motion and attraction. One important result is that water stays liquid across a wide range of everyday conditions on Earth. For a molecule as small as water, one might expect it to become a gas more easily. Many small molecules drift away from one another at temperatures where water still remains liquid. Hydrogen bonding changes that. The molecules attract each other strongly enough that extra energy is needed to separate them widely into vapor. This gives water a much higher boiling point than its small size alone would suggest. The same network affects how water responds to heat. Adding heat to liquid water does not simply make each molecule race away. Some of that energy goes into disturbing and rearranging the hydrogen bond network. Bonds bend, stretch, and break. New ones form. This helps explain why water can absorb a large amount of heat before its temperature changes dramatically. The full story of water and heat belongs to another chapter, but the root of it begins here, in the hidden cost of disturbing molecular connections. Hydrogen bonding also helps explain why water has cohesion. Cohesion means that water molecules tend to stick to one another. This is why a drop can hang from a leaf before it falls, why rain can form round droplets, and why water can be drawn upward through the tiny channels of plants. The molecules are linked through a constantly shifting pattern of attractions. The links are brief, but there are so many of them that the liquid behaves as if it has a quiet internal togetherness. There is also a cooperative quality to this network. A hydrogen bond is not always an isolated event between two molecules. The arrangement of one molecule can influence how its neighbors arrange themselves. When a molecule forms a strong bond in one direction, it can affect the geometry of bonds nearby. The network can therefore carry local patterns through small clusters of molecules, even though those patterns fade quickly. This is one reason liquid water is difficult to describe with perfect simplicity. It is local, dynamic, and collective all at once. Scientists often study water by thinking of these bonds as a network, almost like a graph made of changing connections. In one instant, a molecule may be linked to a certain group of neighbors. A moment later, one link has broken and another has formed. Over time, the network shifts through countless arrangements. Some arrangements are more open, some are more compact. Some resemble the local geometry that appears in ice, while others are more distorted. The liquid contains a moving mixture of local structures, never settling into one fixed design. This is why liquid water is so different from ice. In ice, hydrogen bonds help organize molecules into a more stable crystal pattern. In liquid water, the same tendency toward connection exists, but thermal motion keeps breaking the order apart. The liquid is therefore a compromise between structure and freedom. It remembers the geometry that hydrogen bonding prefers for only tiny moments before motion reshapes it again. That fragile compromise is part of what makes water so versatile. The hydrogen bond network also matters when water meets other materials. Water molecules do not only bond with each other, they can form hydrogen bonds with many other substances that have suitable atoms or charged regions. This allows water to surround and interact with sugars, alcohols, proteins, and many biological molecules. Around such materials, water forms hydration shells, layers of water molecules arranged by their attraction to the surface they touch. These hydration shells are essential in living systems. A protein inside a cell is surrounded by water, and that surrounding water helps influence how the protein folds and moves. Some parts of a protein welcome water because they are charged or polar. Other parts avoid water and tend to tuck inward. The final shape of the protein depends partly on this quiet conversation with the surrounding liquid. Water's hydrogen bonds therefore help shape the machines of life, even when water itself remains in the background. The same idea applies to genetic material, cell membranes, and many chemical reactions. Water creates an environment where molecules can be stabilized, separated, aligned, or brought together. Hydrogen bonds help make that environment responsive. The liquid is never a passive empty space. It is an active participant in chemistry, constantly adjusting its local structure around whatever it contains. This does not mean water has intention or memory in a human sense. Its behavior is physical. The molecules follow forces, motion, temperature, and geometry. Yet the result can still feel almost alive when seen from a distance. Water adapts its structure instantly to surfaces, dissolved substances, heat, pressure, and motion. It does this without planning, through the simple repeated action of molecular attraction. There is beauty in the fact that so much comes from bonds that are individually modest. One hydrogen bond is small. It breaks easily compared with the strong bonds inside molecules. But water contains vast numbers of them. Their collective effect is enormous. The behavior of the liquid emerges from countless brief interactions, each too small to notice alone, each contributing to the whole. A glass of water, then, is a moving pattern held together by attractions that never stop changing. Its calm surface hides a constant molecular negotiation. Every droplet is full of bonds appearing and vanishing. Every ripple moves through a network that is already rearranging itself. And every sip contains an invisible architecture that has shaped the planet for as long as water has existed here. This hidden network is one reason water can be gentle and powerful at the same time. It can soften, dissolve, carry, cool, and flow. It can join molecules together and help pull them apart. It can seem empty while remaining internally rich with motion. For now, you can let the idea settle softly. Beneath the stillness of water, there is endless movement with no need to rush. The network forms, breaks, and forms again, quietly and patiently. Let the day loosen in the same way until your thoughts become as smooth as water resting in the dark. Chapter 4. Why Ice Floats When It Should Sink. There is something quietly astonishing about ice. The same water that flows downward through rivers becomes a solid that rises, and that small reversal helps protect life through winter. Most of the time, when a liquid turns into a solid, its particles settle into a more compact arrangement. They move less, draw closer, and the solid becomes denser than the liquid it came from. This is why we might expect a frozen piece of a substance to sink in its own melt. The solid often carries the same amount of material in a smaller space. Water behaves differently. When it freezes into ordinary ice, it expands. The same amount of water takes up more room as a solid, which means the ice becomes less dense than the liquid water beneath it. Density is a simple idea with deep consequences. It describes how much matter is packed into a given amount of space. A stone sinks in a pond because it is denser than the water it pushes aside. A piece of wood floats because its matter is spread through a larger volume, including tiny spaces inside the material, so it is less dense overall. Ice floats for a similar reason. It contains the same water molecules as liquid water, but in ordinary ice, those molecules are arranged in a more open structure. The reason for that open structure lies in the way water molecules connect with one another as they slow down. In liquid water, molecules move constantly. They form brief attractions with nearby molecules, break away, and form new connections. As water loses heat and approaches freezing, the motion becomes slower. The molecules begin to settle into a more orderly pattern. Hydrogen bonds guide this pattern, encouraging each molecule to hold certain positions relative to its neighbors. In ordinary ice, those positions create an open crystal lattice. The word lattice simply means a repeating structure, a regular arrangement that extends through the solid. The pattern in common ice leaves spaces between molecules. At the molecular level, ice is therefore more spacious than liquid water. Liquid water, by contrast, is disordered enough that some molecules can move into the gaps that would remain open in ice. The liquid can pack more closely, even though its molecules are moving more freely. This is the strange part. We often imagine order as compact and disorder as loose, but water reverses that expectation. The orderly frozen structure spreads molecules apart. The restless liquid state allows them to crowd closer together. Ice is rigid because the molecules are held in fixed positions, yet those positions occupy more space. Liquid water is flexible and flowing, yet at certain temperatures it can fit more molecules into the same volume. This is why ice cubes rise in a glass. Gravity pulls on the ice just as it pulls on everything else, but the surrounding liquid water is denser. The ice displaces water until the upward buoyant force balances its weight. A portion of the ice remains below the surface, while a smaller portion rises above it. What looks casual in a drink is actually a visible result of molecular geometry. This same result becomes far more important in nature. When cold air settles over a lake, the surface water loses heat first. As that water cools, it becomes denser and sinks, while warmer water from below rises to replace it. This mixing can continue for a while, but water has another unusual feature. It reaches its greatest density while it is still liquid at a few degrees above freezing. As it cools further toward freezing, it begins to become less dense again. The coldest water stays near the surface where it can freeze. Because ice floats, the lake freezes from the top downward. A lid of ice forms across the surface. That ice may look like a sign that the whole lake has become still, yet underneath it, the water can remain liquid. The floating ice layer acts as insulation. It slows the loss of heat from the water below to the colder air above. Beneath the frozen surface, fish, insects, plants, and microorganisms can continue to live through the season. This is one of the clearest examples of how a molecular detail becomes an ecological fact. The open structure of ice is invisible to the eye. The hydrogen bonds that guide it are smaller than anything we can sense directly. Yet their result can decide whether a pond remains a winter habitat or freezes solid from bottom to top. A small feature of molecular arrangement becomes a shelter for living systems. Imagine a world where ordinary ice sank. Each time surface water froze, the ice would drop toward the bottom. New water would be exposed to cold air, freeze, and sink as well. In shallow lakes and ponds, this process could continue until much more of the water turns solid. Seasonal freezing would become harsher for aquatic life. Many freshwater ecosystems would be far less stable. The floating of ice gives water bodies a kind of seasonal protection, allowing the coldest layer to stay above while deeper water remains comparatively sheltered. This does not mean every lake is perfectly protected. Very shallow water can freeze deeply. Harsh climates can create thick ice. Salty water behaves differently from fresh water because dissolved salts change freezing behavior and density. Moving rivers have their own complications because flowing water can carry ice, break it, pile it up, or form fragile crystals in turbulent conditions. Still, the basic floating behavior of common ice remains one of the great stabilizing features of water on Earth. Ice floating also shapes climate in a larger way. Sea ice, lake ice, and snow-covered ice reflect a great deal of sunlight. Bright frozen surfaces send more incoming sunlight back into space than dark open water does. When ice cover changes, the amount of absorbed solar energy changes as well. Open water tends to absorb more sunlight, warming more easily, while ice reflects more of it. This feedback can influence local and regional climate patterns, especially in polar regions where ice and ocean meet. At the edge of a frozen sea, this difference is dramatic. Dark water absorbs light and heat. Pale ice reflects it. As ice melts and exposes more water, the surface can absorb more energy, which can encourage further warming and melting. As ice expands, it can increase reflection and reduce absorption. The floating nature of ice makes this possible at the surface, where sunlight arrives. Ice that sank out of sight would interact with the climate very differently. Floating ice also creates habitats of its own. Sea ice may appear empty from above, but its underside and tiny brine channels can support life adapted to cold conditions. Algae can grow in or near ice, becoming part of polar food webs. Animals may depend on the presence, timing, and stability of ice cover. Here again, the physical structure of frozen water becomes tied to biology. There is another quiet consequence in the way ice protects the water below from wind. When a lake is open, wind can stir the surface, mix layers, and increase heat loss. Once ice covers the lake, it separates the water from the moving air. The surface becomes calmer. Under the ice, the liquid world enters a slower state. Light may still pass through if the ice is clear enough and snow cover is thin enough. Life continues, but in a dimmer and colder rhythm. The expansion of freezing water also affects rock, soil, and human structures. Water can enter tiny cracks during warmer conditions. When it freezes, it expands and pushes outward. Over many cycles, that pressure can widen cracks and help break rock apart. This process contributes to weathering in cold regions. It can damage roads, pipes, and buildings as well. The same open crystal structure that lets ice float also gives freezing water the power to press against its surroundings. Ice itself is not always one simple thing. Under different pressures and temperatures, water can form many kinds of ice, with different crystal structures and densities. Some forms exist deep inside icy moons or under extreme laboratory conditions. The ice in a freezer, a lake, or a snowflake is the familiar form that naturally appears at ordinary surface pressure on Earth. Its floating behavior is the one that shapes our daily experience and much of our planet's cold environment. Snow is another expression of ice's structure. Snowflakes form when water vapor becomes solid in cold air, building delicate crystals that reflect the symmetry of molecular arrangement. Their shapes vary with temperature and humidity, creating branching forms that seem almost too intricate for something falling quietly from the sky. Snow gathers into layers full of air spaces, making it even less dense than solid ice. This is why fresh snow can feel soft, muffled, and insulating. What makes ice so beautiful scientifically is that it turns an invisible arrangement into a visible world. You cannot see hydrogen bonds with your eyes, but you can see their consequences when a cube floats in a glass, when a pond freezes only at the surface, when snow brightens a field, or when an iceberg rises above the sea. The large world reveals the small one. So ice floats because water, as it freezes, builds a spacious crystal structure. That structure spreads its molecules apart enough to make the solid less dense than the liquid. From that one fact comes a chain of consequences. Winter lakes remain alive beneath ice, polar surfaces reflect sunlight, cold habitats form, rocks break, landscapes change, and the planet carries winter in a way that life can endure. For tonight, let the image be simple and calm. A lake rests under a quiet sheet of ice. Beneath it, dark water remains liquid, slow, and protected. The cold stays above, the deeper world waits below, and everything becomes still enough for the day to soften and pass. Chapter 5. Water's strange relationship with heat. Water has a remarkable talent for holding heat quietly, and this talent helps make the planet feel steady enough for weather, oceans, bodies, and life to exist. Heat and temperature are easy to confuse because in daily life they often rise and fall together. A hot cup feels hot because energy is moving from the cup into your hand. A cold lake feels cold because energy leaves your skin and enters the water. Temperature describes how energetically molecules are moving on average. Heat is energy being transferred from one place to another because of a temperature difference. Water's strangeness begins with the fact that it can absorb a great deal of heat, while its temperature changes only slowly. This property is called high specific heat capacity. The phrase sounds technical, but the idea is simple. Some substances warm quickly when they receive energy. Others need much more energy before their temperature rises by the same amount. Water belongs to the second group. It is unusually reluctant to heat up quickly, and it is also reluctant to cool down quickly once it has stored warmth. This does not mean water refuses to change temperature. It means the change happens with patience. At the molecular level, this patience comes partly from the attractions between water molecules. When heat enters water, the energy does not simply make each molecule move faster in a straightforward way. Some of that energy is spent disturbing the network of attractions between molecules. Connections bend, stretch, weaken, and reform. The liquid absorbs energy into its internal motion and rearrangement before the average temperature rises much. This is one reason water can act like a thermal cushion. You can sense this in ordinary life. On a summer day, sand at the beach may become painfully hot while the nearby sea remains cool. The sand heats quickly because its particles do not store incoming energy in the same way water does. The ocean absorbs solar energy through a larger moving mass and changes temperature more slowly. Later, after sunset, the sand loses warmth quickly, while the sea releases stored heat more gradually. The same sunlight has touched both surfaces, but their response is very different. This difference helps shape coastal climates. Places near large bodies of water often have milder temperature swings than places far inland. The ocean warms slowly in spring and summer, then cools slowly in autumn and winter. It can soften the extremes of nearby air, making hot days less severe and cold nights less sudden. Wind moving across water carries some of that moderated temperature toward land. A coastline is therefore influenced by water's slow thermal rhythm. On the scale of the whole planet, the effect is enormous. Earth's oceans cover most of the surface and hold a vast amount of water. Because water can store so much heat, the oceans act as the major heat reservoir of the climate system. Sunlight warms the surface, currents move warmth across distances, and deeper mixing carries heat below the top layers. The ocean does not simply sit beneath the atmosphere. It exchanges energy with the air above it, shaping weather patterns, storms, rainfall, and seasonal changes. Ocean currents are one way water's stored heat travels. Warm water can move from tropical regions toward cooler latitudes, while colder water can move in other directions at depth or along different routes. This movement helps redistribute energy around the globe. The atmosphere does some of this work as well, but the ocean carries heat with unusual steadiness because water is dense and thermally generous. A moving current can carry warmth for long distances, slowly releasing it into the air or mixing it into surrounding water. This is one reason some regions are warmer or cooler than their latitude alone would suggest. The temperature of nearby ocean water, the direction of winds, and the behavior of currents can strongly influence local climate. Water's heat storage does not erase the seasons, but it changes their texture. It can delay them, soften them, or make them feel different from one side of an ocean basin to another. Water's relationship with heat becomes even stranger when it changes state. To turn liquid water into vapor, a large amount of energy is needed. The molecules must separate enough to escape the liquid and enter the air as gas. This energy is called latent heat because it is taken in during the change of state rather than appearing as an immediate rise in temperature. When water evaporates from the ocean, a lake, wet soil, or skin, it carries energy with it. This is why evaporation cools. The molecules that escape from a liquid tend to carry away energy, leaving the remaining liquid or surface cooler. When sweat evaporates from your skin, it removes heat from your body. Sweating works best when the air is dry enough for evaporation to happen easily. In humid air, the atmosphere is already holding a great deal of water vapor, so sweat evaporates more slowly and cooling becomes less effective. Evaporation also powers weather. Warm sunlight causes water to evaporate from oceans, lakes, plants, and soil. That water vapor rises or is carried through the atmosphere. When it later condenses into cloud droplets, the energy taken in during evaporation is released back into the air. This release of latent heat can help strengthen rising air, fuel storms, and shape rainfall. A cloud is therefore part of a heat engine, moving energy from Earth's surface into the atmosphere. The water cycle is also an energy cycle. Water rises as vapor after absorbing heat. It condenses after giving heat back. It falls as rain or snow, flows across land, sinks into soil, returns to rivers and oceans, and begins again. At every stage, heat is being stored, moved, released, or absorbed. The familiar movement of water through the planet is inseparable from the movement of energy. Freezing and melting also involve hidden heat. When water freezes, it releases energy to its surroundings as its molecules settle into the structure of ice. When ice melts, it absorbs energy without immediately becoming warmer. This is why melting ice can keep a drink cold. The energy entering the glass is used partly to change ice into liquid water, holding the mixture near the melting point until much of the ice has disappeared. In nature, this matters for snowfields, glaciers, sea ice, and frozen soil. Ice and snow can absorb energy during melting, slowing temperature changes in their surroundings. As long as melting is underway, energy is being spent on the phase change. Once the ice is gone, the same incoming energy can warm liquid water or land more directly. This is one reason the presence or absence of ice can strongly influence local conditions. Water also expands the meaning of heat inside living bodies. Because organisms contain so much water, their temperatures do not swing as quickly as they might if they were made of materials with lower heat capacity. Water helps stabilize internal conditions. Blood, lymph, and the fluid inside cells carry heat from place to place. The body can send warm blood toward the skin to release heat or reduce that flow to conserve it. Water is the medium through which much of this thermal management happens. Plants rely on water's heat behavior too. Water moving upward through stems and leaves carries dissolved minerals, supports pressure inside cells, and participates in cooling through evaporation. When water evaporates from leaf surfaces, it can help regulate leaf temperature. This process also draws more water upward from the roots through the plant's tissues. Even cooking reveals water's thermal personality. A pot of water takes time to boil because it must absorb a large amount of energy. Once boiling begins, The temperature of the liquid water remains nearly steady under ordinary conditions, while energy goes into turning liquid into vapor. This is why boiling water can cook food at a relatively stable temperature. Steam, however, carries substantial energy because vapor formation requires so much heat. When steam condenses on a cooler surface, it releases that energy. This is also why water has long been useful in human technology. It can carry heat through pipes, cool engines, drive turbines as steam, warm buildings, and regulate industrial processes. Its usefulness comes from the same properties that shape oceans and living bodies. Water can absorb, transport, and release energy in a controlled way. It is ordinary enough to be everywhere, yet physically special enough to be one of our most important heat-moving substances. Water's thermal behavior also gives time to the planet. Without the oceans storing and moving heat, Earth's surface would respond more sharply to sunlight and darkness. Days and nights could be harsher. Seasons could swing more abruptly in many regions. Weather systems would be different, and the climate would lack one of its greatest stabilizing influences. Water slows the world down. It gives warmth somewhere to go, and it gives cold something to push against. There is a quiet elegance in this. The same liquid that fills a cup also helps steady the planet's temperature. The same evaporation that cools your skin helps lift energy into storms. The same heat stored in the sea can influence winds, clouds, and rainfall far away. Water's relationship with heat is intimate and planetary at once. So when you feel water warming in sunlight or cooling your hands, you are touching one small part of a much larger story. Water accepts energy slowly, carries it patiently, and releases it in ways that shape both comfort and climate. It is a thermal memory of the world, holding warmth from the sun, from the air, from the body, and from the turning seasons. For now, let that thought become gentle. Somewhere, the ocean is holding the warmth of the day and giving it back slowly to the night. The air softens above dark water, waves move with quiet patience, and the stored heat of the world drifts onward without hurry. Let your own thoughts cool in the same slow rhythm, and allow the day to settle into calm. Chapter 6. The hidden skin on the surface of water. At the surface of water, something strange happens. The liquid seems to form a delicate skin, thin enough to vanish under a touch, yet strong enough to shape droplets, bubbles, rain, and even the lives of small creatures. This skin is not a separate layer floating on top of water. It is water itself, behaving differently because the molecules at the surface experience a different world from the molecules below. Deep inside the liquid, each molecule is surrounded by other water molecules on many sides. It is pulled in different directions by its neighbors, and those pulls mostly balance out. At the surface, the situation changes. Above the surface there is air, with far fewer water molecules to pull upward. The molecules at the top are pulled more strongly sideways and downward into the liquid. This inward pull creates surface tension. Surface tension is the reason the surface of water behaves as though it is slightly stretched. It is why a water droplet tries to become round. It is why a full glass can sometimes hold a small rounded bulge above the rim before spilling. It is why tiny objects can rest on water if they are placed carefully and do not break the surface. The water is still liquid, but its surface resists being stretched or torn. The shape of a droplet reveals this property beautifully. A falling raindrop is often imagined as a teardrop, with a pointed top and rounded bottom. but small droplets are usually closer to round. This happens because a sphere has the smallest surface area for a given amount of liquid. Water molecules at the surface are in a less comfortable position than molecules inside the droplet because they have fewer neighbors to bond with. The droplet therefore tends to reduce the amount of exposed surface. The result is a rounded shape made by countless molecular attractions pulling the liquid into the most compact surface possible. Gravity can distort larger drops, and air resistance can flatten falling rain, but the tendency toward roundness remains clear. On a waxy leaf, water may gather into beads instead of spreading flat. On clean glass, it may spread more easily. The difference comes from the balance between water's attraction to itself and water's attraction to the surface it touches. When water molecules prefer one another strongly, droplets hold together. When they are strongly attracted to a surface, they spread. This balance introduces two important ideas: cohesion and adhesion. Cohesion means water molecules are attracted to other water molecules. Adhesion means water molecules are attracted to another material. Surface tension depends strongly on cohesion. Capillary action, the movement of water through narrow spaces, depends on both cohesion and adhesion working together. Water clinging to a window is adhesion. A droplet holding together is cohesion. Water rising into a thin tube or through a paper towel shows both forces at once. Capillary action may seem to defy gravity at first. Place the edge of a paper towel in water, and the water climbs upward through tiny spaces in the fibers. It does this because water is attracted to the material, and as some water moves along the surface of the fibers, it pulls more water with it through cohesion. The same principle helps water move through soil and into fine spaces in plant tissues. In tall plants, many processes work together to move water upward, including evaporation from leaves and tension in the water column. But capillary behavior is part of the larger story of how water interacts with narrow passages. The surface of water also supports some forms of life in a remarkable way. Water striders, those thin-legged insects that move across ponds, do not truly walk on a solid skin. Their legs press down on the surface without immediately breaking it. The surface bends beneath them, and surface tension provides an upward support. Their legs are shaped and textured in ways that help spread their weight and repel water. They are light enough and adapted enough to live at the boundary between liquid and air, using a property of water that larger animals can only notice from the outside. A small needle or paper clip can also rest on water under careful conditions, even though metal itself is denser than water. It floats only because the surface has not been broken and because the object's weight is spread gently across the surface. Once the surface is disturbed, or once the object becomes wet in the wrong way, it sinks. It is a delicate effect, powerful on small scales and easily overcome on larger ones. Scale matters greatly. Surface tension is most noticeable when objects are small because the relative importance of surface forces increases as size decreases. For a large animal, gravity dominates. For a tiny insect, surface forces can become a major part of the environment. In the world of small bodies, drops, fibers, pores, and insect legs, water's hidden skin becomes a landscape. It can support, trap, pull, cling, and guide movement. Soap changes this landscape. When soap or detergent enters water, its molecules gather at surfaces and interfere with the strong attraction between water molecules. This lowers surface tension. That is why soapy water spreads more easily and can wet oily or dirty surfaces better than plain water. Soap molecules have one part that interacts well with water and another part that interacts better with oils and greasy materials. By lowering surface tension and helping water interact with substances it would otherwise avoid, soap makes cleaning possible. This is also why soap helps form bubbles. A bubble is a thin film of water stabilized by soap molecules, with air on both sides of the film. Pure water can form brief films, but they usually break quickly because surface tension pulls the liquid together and drains the film. Soap reduces that tension and helps the film stretch without snapping immediately. The shimmering colors on a soap bubble come from light reflecting from the thin surfaces of the film. Different thicknesses interfere with light in different ways, creating shifting bands of color as the film drains and changes. Foam is a crowd of bubbles, and it too depends on surface behavior. Sea foam, bath foam, and the foam on certain drinks all involve thin liquid films surrounding pockets of gas. The exact stability of foam depends on the substances dissolved in the water, the size of bubbles, drainage, evaporation, and how easily films rupture. Water's surface tension sets the stage, while other molecules decide how long the performance lasts. Surface tension also shapes the beginning of rain. In clouds, water vapor condenses onto tiny particles such as dust, salt, or other aerosols. Small droplets form, collide, merge, and grow. Surface tension helps hold each droplet together as it develops. Very tiny droplets face a special challenge because curved surfaces affect how easily molecules remain in the liquid phase. A soft rainstorm begins with countless tiny boundaries between water and air. Even the edge of water in a glass has a surface story. If you look closely at water against the wall of a clean glass, the surface curves upward near the edge. This curve is called a meniscus. It appears because water is attracted to the glass, and that adhesion pulls the liquid slightly upward along the wall. The rest of the surface responds through cohesion and surface tension, forming a smooth curve. In a narrow tube, this effect can become strong enough for water to rise noticeably. In soil, surface tension and capillary action help determine how water is held between grains. After rain, water does not simply fall straight downward and vanish. Some clings to mineral surfaces. Some gathers in small pores. Some moves through connected spaces. The size of the pores, the chemistry of the surfaces, and the amount of water already present all influence movement. This helps explain why different soils drain differently and why plants can draw water from spaces too small for us to see. The hidden skin of water also affects human bodies in subtle ways. Tears spread across the eye because surface forces, oils, salts, and blinking work together to create a smooth protective layer. Saliva wets food and surfaces in the mouth. In the lungs, surface tension becomes especially important because tiny air sacs must remain open as we breathe. The body uses natural surfactants to reduce surface tension there, helping breathing happen with less effort. Without this chemical control, the delicate surfaces inside the lungs would behave very differently. So the surface of water is not just the place where water ends. It is a place where the liquid negotiates with air, solids, oils, glass, leaves, skin, and living bodies. At every boundary, water behaves according to a balance of molecular attraction. Sometimes it beads, sometimes it spreads, sometimes it climbs, sometimes it forms films, droplets, bubbles, or curved edges. The surface is active, responsive, and full of small decisions made by physics. This is why a single droplet can hold so much meaning. It is a tiny sculpture created by attraction. Its roundness comes from molecules trying to reduce exposed surface. Its cling to a leaf comes from adhesion. Its trembling edge comes from the constant motion of molecules and the pull of gravity. It looks simple because it is small, but it contains a complete lesson in how matter behaves at boundaries. Water's hidden skin reminds us that the most ordinary surfaces are never empty. The top of a pond, the bead on a window, the curve in a glass, the film of a bubble, and the shimmer of rain on leaves all carry the same quiet principle. Water is always being shaped from within by its own molecular attraction, and from without by the world it touches. For now, let that image become peaceful. Picture a still pond at night, its surface holding the reflection of the sky, delicate but unbroken. A small ripple passes across it and fades. The water settles again, smooth and patient, and the day can settle with it. Chapter 7. The liquid that dissolves the world. Water does something more powerful than simply flow across the planet. It quietly takes pieces of the world into itself and carries them onward. This ability is so familiar that it often goes unnoticed. Sugar disappears into tea, salt vanishes into soup, minerals seep from stone into groundwater, nutrients move through blood. Rain touches soil and comes away changed. A river begins as falling water, yet by the time it reaches the sea, it has become a moving chemical mixture, carrying traces of mountains, forests, farms, cities, and ancient rock. Water rarely travels empty. Wherever it goes, it gathers something. This is why water is often called a universal solvent. The phrase is useful, but it should not be taken too literally. Water does not dissolve everything. Oil resists it. Wax resists it. Many rocks surrender only tiny amounts over long stretches of time. Still, compared with most common liquids, water dissolves an extraordinary range of substances. It is especially good at dissolving salts, minerals, acids, bases, sugars, and many polar molecules. This dissolving power is one of the reasons water is so important for geology, weathering, cooking, medicine, and life. The source of this power is water's electrical nature. A water molecule is neutral overall, yet its charge is unevenly distributed. The oxygen side has a slightly negative character, while the hydrogen side has a slightly positive character. Because of this, water molecules can turn themselves toward charged particles in useful ways. If a positive ion is present, the oxygen side of nearby water molecules is attracted to it. If a negative ion is present, the hydrogen side points toward it. The liquid surrounds the dissolved pieces with tiny shells of oriented water molecules. This is what happens when table salt dissolves. In the dry crystal, positive sodium ions and negative chloride ions are held together in a regular arrangement. When the crystal meets water, water molecules begin to gather around the ions at the surface. Their opposite charges pull at the salt structure. If the attraction between water and the ions is strong enough to overcome the attraction holding the crystal together, the ions separate and drift into the liquid. Once surrounded by water molecules, they remain spread out rather than immediately locking back into the crystal. To the eye, the salt seems to disappear. At the molecular level, it has not vanished. It has separated into charged particles too small to see, each surrounded by moving water molecules. The water has changed the form in which the salt exists. Instead of a hard grain, it becomes a dissolved presence throughout the liquid. This is why a spoonful of salt can flavor an entire pot of soup. The material spreads because water allows its particles to move separately. Water dissolves sugar in a different way. Sugar molecules do not break apart into ions the way table salt does, but they have regions that can interact well with water. Water molecules surround the sugar molecules and pull them away from the crystal surface. The sugar remains chemically sugar, but it becomes dispersed through the liquid. This is why sweetness can spread evenly through tea or coffee after stirring. The water has separated the sugar molecules and carried them through the drink. The same principle shapes the natural world on much larger scales. Rainwater is never just pure water for very long. As it falls through the air, it can absorb gases and tiny particles. When it reaches the ground, it seeps through soil, where it encounters decaying leaves, minerals, roots, microbes, and gases produced by living organisms. As it moves downward, it can dissolve small amounts of rock and carry those dissolved substances into streams, springs, aquifers, and rivers. This slow dissolving is one of the quiet engines of landscape change. Water reacts with minerals in rock, loosening atoms and ions from solid structures. Over time, this chemical weathering helps break down mountains and create soil. Some rocks dissolve more easily than others. Limestone, for example, can be carved by slightly acidic water into caves, sinkholes, and underground channels. The cave does not appear because water simply scratches at the rock from the outside. It grows because water carries the rock away in dissolved form, drop by drop, season by season. Groundwater is therefore a hidden chemical traveler. It moves through cracks, pores, and layers beneath the surface, collecting minerals along the way. This is why spring water can taste different from one place to another. It has passed through different rocks and soils. The taste may come from dissolved calcium, magnesium, sodium, bicarbonate, or other substances. Even clear water can contain a record of the ground it crossed. Rivers carry this record toward the ocean. Every river is a moving solution, as well as a moving body of water. It carries visible sediment, such as sand and clay, but it also carries dissolved material that cannot be seen. These dissolved substances eventually help shape the chemistry of lakes and seas. The ocean's saltiness is partly the result of long-term delivery of dissolved ions from land, along with processes at the seafloor and the removal of some materials by biological and geological activity. The sea is not salty by accident. It is the result of immense time, constant transport, and the ability of water to dissolve the crust of the planet in tiny portions. Inside living organisms, water's dissolving power becomes even more intimate. Cells are filled with water-based fluid containing salts, sugars, amino acids, proteins, and many other molecules. Reactions inside cells depend on substances being able to meet one another, move, separate, and change. Water provides the medium for this motion. It allows ions to carry electrical signals. It helps nutrients travel. It helps waste products leave. It helps large biological molecules fold into useful shapes by favoring some interactions and discouraging others. Blood is another example. It is not just red liquid moving through vessels. It is a complex water-based transport system. Water in blood plasma carries dissolved salts, nutrients, hormones, gases, and waste products. Some substances dissolve directly. Others travel attached to specialized molecules. Either way, the watery nature of blood allows the body to distribute materials to tissues and remove what those tissues no longer need. The ability of water to dissolve and carry matter is part of what keeps the body chemically connected. Digestion also depends on water. Food must be softened, broken apart, mixed, and chemically processed. Water helps dissolve flavor molecules, salts, sugars, and nutrients. It allows enzymes to work in a fluid environment. It helps carry digested materials through the body. Even taste depends partly on dissolving. A dry tongue cannot taste properly because molecules from food must dissolve in saliva before they can interact with taste receptors. Water turns matter into information for the body. In plants, water carries minerals from soil into roots and upward through tissues. Dissolved nutrients move with the water stream, reaching leaves and growing cells. Water also transports sugars produced in leaves to other parts of the plant through specialized tissues. A tree is therefore partly a system for moving dissolved substances through a living structure. The trunk may look solid and still, but inside it, water connects roots, leaves, growth, and survival. The power to dissolve also gives water a dangerous side. Because water carries substances so effectively, it can also carry pollutants. Chemicals from industry, agriculture, mining, and cities can enter rivers and groundwater. Some dissolve easily and travel far. Others attach to particles or collect in living tissues. Water's gift as a transporter becomes a problem when harmful substances enter the system. The same property that carries nutrients can carry contamination. This is why water quality matters so deeply. Clear water is not always clean water. Some dissolved substances are invisible, tasteless, or present at levels that require careful testing. A stream can look peaceful while carrying too much nitrate, heavy metal, salt, or organic chemical. Understanding water as a solvent helps explain why protecting rivers, lakes, and aquifers is more than keeping them visually beautiful. It is about protecting the invisible chemistry moving through them. Water's dissolving power also affects everyday objects. It can corrode metals by supporting chemical reactions. It can leave mineral scale behind when hard water evaporates. It can stain walls, weaken building materials, and carry cleaning agents into fabrics. When water dries on glass, it may leave rings or spots because dissolved minerals remain after the liquid has evaporated. The water disappears into air, but what it carried stays behind. This is one of the easiest ways to notice that water is rarely empty. A drop dries and a faint mark remains. A kettle develops scale. A cave grows a stalactite as mineral-rich water drips and leaves material behind. A shell forms from dissolved ingredients taken from seawater. Dissolving and depositing are partners. Water takes material into itself in one place and leaves it somewhere else. In this way, water acts almost like a quiet editor of the physical world. It softens some boundaries, separates some materials, transports others, and slowly rewrites surfaces. It turns rock into ions, soil into solution, food into nourishment, and waste into something that can be carried away. It does all this without forceful drama. The work is often slow, clear, and silent. So water dissolves the world because its molecules can surround charged and polar substances, separate them from solids, and keep them moving in liquid form. This property links a spoon of salt to the saltiness of oceans, a cup of tea to the chemistry of cells, a raindrop to the carving of caves, and a river to the long memory of mountains. For now, let that thought become quiet. Imagine water moving through stone, through soil, through roots, through rivers, carrying only what it can hold and leaving the rest behind. Let the day dissolve gently in the same way, piece by piece, until what remains is simple, clear, and still. Chapter 8. Water's Secret States: Supercooled, Pressurized, and Strange. Water seems familiar because we usually meet it in only a few forms, yet beyond ordinary experience it can become colder than freezing, denser than expected, and stranger than almost any everyday substance suggests. Most of us learn water through simple categories. Liquid water fills a glass. Ice forms in a freezer. Steam rises from a kettle. These forms feel complete, as though water has only 3 ordinary ways of existing. But those familiar forms are only the surface of a much wider story. Change the temperature, change the pressure, remove dust, compress the ice, or trap water in an unusual environment, and its behavior begins to move into hidden territory. The first strange state is supercooled water. Under normal everyday conditions, liquid water freezes when it reaches its freezing point. In the real world, however, freezing usually needs a starting point. Ice crystals often begin forming around a tiny particle, a scratch, a bubble, a speck of dust, or an existing piece of ice. These starting points are called nucleation sites. They give water molecules a place to begin arranging themselves into the ordered pattern of ice. When very pure water is cooled carefully and kept free from strong disturbances, it can remain liquid below its usual freezing point. This is supercooled water. It is colder than ordinary liquid water should be, yet it has not crystallized. The molecules are moving slowly enough that ice would be stable, but the first stable crystal has not formed. The liquid is balanced in a fragile state, waiting for the right disturbance. A bottle of very pure, very still water can sometimes show this effect. It may look completely liquid while sitting below the normal freezing temperature. Then a tap, a shake, or contact with a small ice crystal can trigger rapid freezing. The change can spread through the water almost like a visible wave. Nothing magical has happened. The water was already cold enough to freeze. It simply lacked the right starting point until the disturbance arrived. Supercooled water is also important in the atmosphere. Clouds can contain droplets of liquid water at temperatures below freezing. These tiny droplets may remain liquid until they encounter particles, ice crystals, or conditions that allow freezing to begin. This matters for weather because the freezing of droplets releases heat and changes the structure of clouds. It also plays a role in the formation of snow, sleet, freezing rain, and ice buildup on surfaces. Freezing rain is one familiar result of water's ability to remain liquid while cold. In some weather conditions, droplets can fall as supercooled liquid and freeze when they strike roads, branches, wires, or aircraft surfaces. The water changes state on contact, creating a glaze of ice. The danger comes from the same principle that makes supercooled water fascinating. A liquid can carry cold silently until the right surface gives it a place to become solid. Water becomes even stranger under pressure. At the surface of Earth, we experience a narrow range of pressures, so it is easy to assume that melting, boiling, and freezing are controlled mostly by temperature. Pressure matters too. Increase pressure, and molecules are forced into different arrangements. Lower pressure, and boiling can happen more easily because the liquid has less outside force holding it together. This is why water boils at a lower temperature high in the mountains than it does near sea level. In a pressure cooker, the opposite happens. The sealed environment allows pressure to rise, so liquid water can become hotter before it boils. Food cooks faster because the water and steam inside can reach temperatures above the usual boiling point at ordinary air pressure. This is not a different kind of water in the exotic sense, but it shows the larger truth. Temperature alone decides water's state. pressure changes the rules. The deepest strangeness appears when pressure reshapes ice. The ice we see in freezers, snowfields, and frozen lakes is only one common arrangement of water molecules. Under higher pressures and different temperatures, water can freeze into other forms of ice. These forms have different crystal structures. Some are denser than ordinary ice. Some arrange the same water molecules into patterns that would never appear naturally in a kitchen freezer. This means ice is not one single substance in the simple everyday sense. It is a family of solids made from water molecules arranged in different ways. Ordinary ice is the familiar member of the family, light enough to float and open in structure. Under pressure, the molecules can be pushed into more compact patterns. The hydrogen-bonded network bends into new geometries. The solid may become denser, harder, and structurally different, even though it is still made of water. These high-pressure ices are not common on Earth's surface, but they may matter greatly inside icy worlds. Large moons and distant planetary bodies can contain layers of water ice under enormous pressure. Deep below their surfaces, ice may no longer be the fragile floating material we know. It may become a dense mineral-like solid, stacked in hidden layers above or below subsurface oceans. In such places, water's secret states may help shape the interiors of worlds far from the sun. Pressure also affects liquid water in the deep ocean. At great depths, water is squeezed by the weight of everything above it. It remains liquid because temperature, pressure, and dissolved substances combine to keep it that way. Near hydrothermal vents, seawater can become extremely hot while staying liquid under pressure. At the surface, water heated so strongly would turn quickly into vapor. In the deep sea, pressure helps hold the fluid together, allowing hot water to flow from cracks in the seafloor and carry dissolved minerals into the ocean. Under even more extreme conditions, water can enter a state called supercritical water. In this state, the usual boundary between liquid and gas disappears. The water is hotter than its critical temperature and under pressure higher than its critical pressure. It no longer behaves exactly like an ordinary liquid or an ordinary vapor. It can flow like a dense gas while dissolving certain materials more like a liquid. This state is mostly encountered in specialized industrial settings, scientific research, and some extreme natural environments. Supercritical water helps reveal how much our ordinary categories depend on everyday conditions. We think of liquid and gas as separate states because that is how they appear around us. But under extreme heat and pressure, the distinction can fade. Water becomes a fluid that does not fit neatly into the familiar picture of a puddle or a cloud. Its behavior shifts because the molecules are packed and energized in a way that ordinary life rarely shows us. There are also forms of ice that lack the neat order of ordinary crystals. These are called amorphous ices. In a crystal, molecules are arranged in a repeating pattern. In amorphous ice, the molecules are frozen into a more disordered arrangement, more like a solid glass made of water. Such ice can form under certain conditions, including very cold environments where water vapor freezes quickly, or where ice is compressed and transformed. In space, where temperatures can be extremely low, amorphous ice may be widespread on grains, comets, and icy surfaces. This is another reminder that water beyond Earth does not always look like the water we know. In space, water can be vapor, crystalline ice, amorphous ice, or locked inside minerals. On icy moons, it may exist as surface ice, deep ocean, high-pressure ice, or salty liquid hidden below a frozen crust. Around young stars, water ice can coat tiny dust grains that later become part of planets and comets. The same molecule participates in many environments, taking different forms as conditions change. Even ordinary water has a phase diagram, a map of the states it prefers under different combinations of temperature and pressure. The map is far more complex than a simple triangle of solid, liquid, and gas. It includes boundaries where one state gives way to another, regions where unusual ices become stable, and points where familiar distinctions blur. The phase diagram of water is like a secret atlas, showing countries of matter that daily life rarely visits. The reason water can have so many faces is that its molecules are small, polar, and able to form directional attractions. Under ordinary conditions, these features give water its familiar properties. Under extreme conditions, the same features allow many possible arrangements. The molecule does not change its identity, but the collective pattern changes. Water shows how one simple building block can create many forms when the environment presses, cools, heats, or confines it. This matters scientifically because water is central to planets, climate, geology, and life. To understand water only as the liquid in rivers would be to miss much of its behavior. Clouds may hold supercooled droplets. Glaciers contain ice shaped by pressure and time. Deep oceans can hold hot pressurized fluids. Icy moons may hide layers of unfamiliar ice. Space may contain disordered frozen water that has never flowed as a liquid. Water is familiar on Earth's surface, but across nature it is a shapeshifter. And yet there is comfort in that strangeness. The water in a glass is part of a larger family of possibilities. It is the calm, ordinary face of a substance capable of surviving cold, pressure, darkness, heat, and deep time. It can rest as snow, hide beneath ice, drift as vapor, sleep inside comets, or move through the blackness around distant worlds. For now, let that thought become quiet and wide. Water does not have to stay in one form to remain itself. It changes with its surroundings, adapts to pressure, softens into liquid, hardens into ice, and vanishes into vapor. Let the day change in the same gentle way, loosening its shape until only stillness remains. Chapter 9. How Water Moves: Waves, Rivers, Vortices, and Chaos. Water is never truly still for long because the same liquid that rests quietly in a glass can also roll across oceans, carve through stone, spin into vortices, and turn simple motion into deep complexity. Movement is one of the ways water reveals its hidden nature. A smooth pond may look calm, but even there the surface responds to the smallest touch of air, falling leaves, insects, and temperature differences. Water is sensitive to forces. It yields easily, but it also carries motion onward. Push it gently and a ripple travels. Pour it from a cup and it folds around itself. Let rain gather on a hillside and it begins to search for a path downward. The motion of water begins with a simple fact. Water flows because forces act on it. Gravity pulls water downhill. Wind drags across the surface of lakes and oceans. The moon and the sun raise tides through their gravitational pull. Differences in temperature and saltiness can make some seawater denser than other seawater, helping drive deep currents. The shape of land and seafloor guides the path. Water obeys these forces, yet the results are often far from simple. A wave is one of the clearest examples. When wind blows across water, it transfers energy to the surface. Small ripples can grow into larger waves if the wind is strong enough, steady enough, and has enough open distance over which to act. The wave may travel across a lake or ocean, but the water itself does not usually race forward with the wave in the way it appears to from the shore. In deep water, the water particles mostly move in looping paths as the wave passes. This is why a floating object can bob up and down as waves go by without being carried forward as fast as the wave crests. The wave is mainly a traveling pattern of energy. The water moves locally, while the disturbance moves onward. This distinction is easy to miss because the surface looks as if the whole ocean is rushing toward land. As waves approach shallow water, the seafloor begins to matter. The lower part of the wave feels the bottom and slows down. The upper part keeps moving faster for a while, so the wave steepens. Eventually, it becomes unstable and breaks. The smooth rising wall collapses into foam, sound, and turbulence. A breaking wave is water losing its orderly shape. Energy that traveled across open water is suddenly transformed into swirling motion. Bubbles, spray, and heat spread through the moving fluid. Rivers show another kind of movement. A river begins when water collects from rain, springs, melting snow, or groundwater and finds a path downhill. Gravity gives it direction, but the land gives it character. A steep mountain stream moves quickly, tumbling over rocks and carrying gravel. A broad lowland river may move more slowly, curving across a floodplain and carrying fine sediment. The river is always adjusting to slope, volume, rock, soil, vegetation, and obstacles. A river does not simply pass over a landscape, it reshapes the landscape as it moves. Flowing water can lift particles from the riverbed, carry them downstream, and deposit them somewhere else. During storms, when the flow becomes stronger, a river can transport much more sediment than it does during quiet conditions. Mud, silt, sand, pebbles, and sometimes larger stones may all be part of the river's work. The visible water is only part of the river. The moving sediment is part of its body too. Over time, this movement carves valleys, widens channels, builds deltas, and changes the position of river bends. In a curving river, faster flow often presses against the outside of a bend, where erosion can deepen and cut the bank. Slower flow near the inside of the bend can allow sediment to settle. The river gradually migrates, making loops that may grow wider until they are cut off and become quiet crescent-shaped lakes. A river is therefore a moving line that edits the land through time. The motion inside a river is rarely uniform. Near the banks and bottom, friction slows the water. Near the center and surface, it may move faster. Rocks, roots, channel bends, and changes in depth create eddies and small circulating regions. The river has layers of speed and direction hidden inside it. To the eye, the surface may show only waves and ripples, but below that surface, the flow may twist, accelerate, separate, and rejoin. Sometimes water moves smoothly in layers. This kind of motion can happen when flow is slow and orderly. One layer slides past another with little mixing, but as speed increases, or as the path becomes rougher and more complicated, the motion can become turbulent. Turbulence is the swirling, irregular motion seen in rapids, breaking waves, storm drains, waterfalls, smoke-like mixing in rivers, and the white churn beneath a spillway. Turbulence is one of the great difficult problems in physics. The basic rules governing fluid motion are known, but the behavior that emerges can be wildly complex. Small differences can grow into large changes. Swirls create smaller swirls, which create still smaller swirls, passing energy down through scales until it is finally dissipated. A stream pouring from a tap may begin smooth, then break into irregular motion. A river rapid may seem random, yet it is shaped by the water's speed, depth, rocks, and channel form. This is where water becomes both beautiful and hard to predict. A vortex forms when water rotates around a center. You can see one in a draining sink, in an eddy behind a rock, or in a whirlpool where currents meet. The spinning motion may begin from a slight imbalance in flow. Once rotation begins, the surrounding water can feed it, stretch it, or break it apart. Vortices can be tiny and brief, or large enough to shape currents in the ocean. A vortex is not a solid object, yet it behaves almost like one for a time. It has a recognizable shape. It can move, merge with other vortices, weaken, or shed smaller swirls from its edges. In rivers, eddies behind rocks create resting places for fish and patterns of sediment deposition. In the ocean, enormous rotating features can carry heat, salt, nutrients, and living organisms across long distances. A swirl is a pattern made of motion, held together only as long as the flow continues to support it. Water's motion is also shaped by viscosity. Viscosity is a fluid's internal resistance to flow. Honey has high viscosity and moves slowly. Water has much lower viscosity, so it flows easily, yet it has resistance too. Its small amount of viscosity matters because it helps transfer motion between layers and eventually turns organized movement into heat. With viscosity, flow can grip surfaces, slow near walls, and lose energy over time. The interaction between water and boundaries is everywhere. In a pipe, the water near the wall is slowed by contact with the surface. In a stream, the bed and banks shape the flow. In the ocean, the seafloor, coastlines, and islands steer currents and disturb waves. Even air above the water is a boundary of sorts because wind can pull at the surface and raise waves. Water's motion is never only about the water. It is about everything touching it. Rain reveals the smaller scale of this motion. A drop falling into a puddle sends a circular ripple outward. If rain falls heavily, ripples collide, interfere, and erase one another. Thin sheets of water can run across pavement, gather into channels, and suddenly become miniature rivers along a curb. Waterfalls show the conversion of energy with particular clarity. Water at height has gravitational potential energy. As it falls, that energy becomes motion. At the bottom, the falling water strikes the pool, creating bubbles, spray, sound, turbulence, and currents. The impact can carve plunge pools into rock over long periods. What looks like a graceful curtain is also a machine for transforming height into motion and motion into erosion. In the ocean, movement becomes planetary. Surface currents can be driven by wind and shaped by Earth's rotation, coastlines, and basin geometry. Deeper currents can be influenced by density differences caused by temperature and salt content. Together, these motions help move heat, oxygen, nutrients, and dissolved substances through the sea. The ocean is a vast moving system with surface waves, tidal flows, deep circulation, eddies, and mixing all happening at once. This constant motion matters for life. Moving water brings oxygen to aquatic organisms, carries food particles, spreads larvae, moves nutrients, and removes waste. In rivers, flow creates habitats ranging from quiet pools to fast riffles. In oceans, currents help connect ecosystems separated by enormous distances. Even microscopic life drifts with currents, living inside the motion of the water around it. Water's movement can also be destructive. Floods occur when water exceeds the capacity of channels, soils, or drainage systems. Fast-moving water can lift cars, undermine roads, erode banks, and carry debris. The danger comes from water's mass and momentum. A shallow flow can be powerful when it moves quickly. A river in flood is deeper, faster, heavier, and full of force. Yet the same motion that threatens also renews. Floods can deposit fertile sediment. Rivers can rebuild wetlands. Waves can shape beaches. Currents can distribute nutrients. Movement is part of water's role as a planet-shaping substance. Stillness is only a pause between forces. So water moves because it is responsive. It receives energy from wind, gravity, tides, pressure differences, and the shape of the world around it. It turns that energy into waves, currents, rivers, vortices, and turbulence. Sometimes the motion is smooth enough to look peaceful. Sometimes it becomes so complex that even advanced mathematics struggles to follow every detail. For now, imagine a slow river under evening light. Small ripples pass around stones. A quiet eddy turns near the bank. Far away, waves cross a dark ocean, carrying energy through the night. Water keeps moving without hurry, and you can let your thoughts move the same way, softening, circling, and finally becoming calm. Chapter 10. Why water may be the key to life in the universe. When scientists look for life beyond Earth, they often begin with water, because this familiar liquid may be one of the simplest signs that chemistry has found a place to become alive. Water by itself is only a molecule made from hydrogen and oxygen, moving through different states under different conditions. A frozen moon can contain water and still be empty of biology. A distant planet can have clouds and seas and still remain lifeless. Yet every living thing known on Earth depends on water so deeply that it is difficult to imagine life here without it. Water is the medium in which cells work, the fluid that carries nutrients, the environment where countless reactions unfold, and the substance that helps living systems stay organized while the world around them keeps changing. The reason water matters begins with chemistry. Life is a network of reactions, structures, boundaries, energy flows, and information. Molecules must meet, they must separate, they must change shape, exchange parts, release energy, store energy, and build larger patterns from smaller pieces. For this to happen, there needs to be a fluid environment where molecules can move without drifting away completely. Water is unusually good at creating that environment. Because water is polar, it can surround many charged and polar substances and keep them distributed through a liquid. Salts can separate into ions. Sugars can spread. Many biological molecules can fold, unfold, react, and be transported. Inside cells, water allows dissolved materials to move from one place to another. It helps chemical signals travel, supports the shape of proteins, and provides the surrounding medium for the reactions that keep the cell alive. A cell is often imagined as a tiny bag of liquid, but it is more organized than that. It contains membranes, molecular machines, genetic material, structural elements, and controlled chemical pathways. Water fills much of the space between those parts, yet it also interacts with them. Some regions of molecules are comfortable in water, others avoid it. This difference helps membranes form and helps proteins take useful shapes. Water helps create order by deciding which parts of molecules can remain exposed and which parts tend to hide away. This is especially important for cell membranes. The molecules that form many biological membranes have one part that interacts well with water and another part that avoids it. When placed in water, they can arrange themselves into thin barriers, with water-friendly regions facing outward and water-avoiding regions tucked inward. Such barriers are essential because life needs separation. A cell must have an inside and an outside. It must control what enters, what leaves, and what stays. Water helps make that boundary possible. Water also helps life manage heat. Living chemistry works best within certain temperature ranges. Too cold and reactions may slow dramatically. Too hot and delicate molecules can lose their structure. Water's ability to absorb heat slowly helps stabilize environments and organisms. Oceans resist rapid temperature change. Bodies rich in water can buffer sudden heating and cooling. This steadiness gives life time to function, adapt, and maintain internal balance. Another key feature is that water can remain liquid across a wide range of temperatures under the right conditions. Liquid matters because solids can lock molecules in place, while gases can spread them too thinly. A liquid is a middle ground. Molecules can move and meet, but they remain close enough for chemistry to continue. On Earth, this middle ground has been central to life. Oceans, lakes, groundwater, wet soil, and the watery interior of cells all show how important liquid environments can be. This is why the search for life elsewhere often follows water. On Mars, dry valleys, minerals shaped by water, ancient lake beds, and river-like channels tell a story of a planet that once had liquid water on its surface in at least some places and times. Mars today is cold and dry at the surface, with a thin atmosphere. But evidence of past water makes it one of the most studied worlds in the search for ancient habitability. The question is whether it ever had liquid water, useful chemistry, energy, and enough stability for life to begin or persist. Beyond Mars, some of the most intriguing places are icy moons. A moon covered in ice may seem lifeless at first glance, especially far from the warmth of the sun. But ice can hide liquid water below. Gravitational squeezing from a giant planet can flex a moon's interior, producing heat. Radioactive decay in rock can add more warmth. Salts and other dissolved materials can lower freezing points and change the behavior of the ocean. Beneath an icy crust, there may be a dark sea in contact with rock. This contact with rock matters. On Earth, deep ocean environments show that life can exist without sunlight, using chemical energy from reactions between water, rock, and dissolved substances. Hydrothermal systems on the seafloor release warm, mineral-rich fluids into the ocean. Around them, ecosystems can form through chemistry rather than direct sunlight. This does not prove that life exists in subsurface oceans beyond Earth, but it shows that darkness alone does not make life impossible. If liquid water, useful chemistry, and energy exist together, a hidden ocean becomes scientifically interesting. Europa, one of Jupiter's moons, is a powerful example. Beneath its cracked, icy surface, scientists think there is a global salty ocean. The surface is harsh, cold, and exposed to radiation, but the ocean below may be protected by ice. If material can move between the surface, the ice shell, and the ocean, chemical ingredients may be exchanged. If the ocean also touches a rocky seafloor, reactions there could provide energy sources. These are reasons Europa is considered a major target in astrobiology. Enceladus, a moon of Saturn, is another striking example. It sends plumes of water vapor and icy particles into space from its south polar region. Those plumes allow a distant spacecraft to sample material that may come from a subsurface ocean without landing on the moon. The detected ingredients include salts and organic molecules, showing that the ocean is chemically rich. Again, this is not the same as finding life. It means the environment has several features that make the question worth asking carefully. Water also shapes how scientists think about planets around other stars. A planet in the right range of distances from its star may have surface temperatures that allow liquid water, depending on its atmosphere, pressure, clouds, composition, and history. This region is often called the habitable zone. The idea is useful, but it is only a starting point. A planet can be in that zone and still be barren. It may have lost its atmosphere. It may have too much greenhouse heating. It may lack the chemical cycles needed for long-term stability. This is a careful point. Water may be necessary for life as we know it, yet water alone does not guarantee life. A sterile ocean is possible. A wet world can remain chemically quiet. Life needs energy, useful elements, suitable conditions, and time. It may also need environments where molecules can concentrate instead of being diluted endlessly. Shorelines, pores in rock, ice boundaries, mineral surfaces, wet and dry cycles, and hydrothermal systems have all been considered as possible settings where early chemistry might become more complex. The origin of life on Earth remains an open scientific question. Researchers study many possibilities, from warm ponds to deep-sea vents, from mineral surfaces to icy environments. What unites many ideas is the importance of water as a medium and participant. It can dissolve ingredients, carry them, separate them, and allow reactions to occur. At the same time, too much water can make some chemical steps harder because certain bonds form more easily when water is removed. This means the relationship between water and life is subtle. Water supports life, but the path from chemistry to biology likely required special environments where conditions changed over time. Water also provides protection and continuity. In oceans, it shields life from some environmental extremes. In ice-covered habitats, it can remain liquid below a frozen surface. In small organisms, it allows internal chemistry to stay connected. Water does not make life simple, but it gives complexity a place to unfold. It allows matter to become mobile without becoming scattered. It allows boundaries to form without complete isolation. It allows energy to move through systems without destroying them immediately. From a cosmic perspective, water is made from common elements. Hydrogen is the most abundant element in the universe, and oxygen is produced in stars and spread into space through stellar evolution. Water has been detected in many cosmic environments, from molecular clouds to comets and planetary systems. Water is special in its properties, yet its ingredients are widespread. Still, the presence of water in space does not mean the universe is full of life. Much water is frozen, dispersed, trapped, or locked in conditions that may never allow biology. The real mystery lies in where water becomes liquid, stable, chemically active, and connected to energy. Those are the places that draw attention. A damp rock, a vanished Martian lake, an ocean under ice, or a distant planet with possible clouds can each become part of the same search. In the end, water may be the key to life in the universe because it is both ordinary and extraordinary. It is made from simple atoms, yet it supports complex chemistry. It flows easily, yet it can organize molecules. It dissolves materials, carries heat, forms boundaries, shapes planets, and fills cells. On Earth, life did not merely use water as a background. Life grew inside water's possibilities. For now, let that thought open gently and then grow quiet. Somewhere water may be resting under ice on a distant moon, drifting as vapor around a young world, or lying hidden in the minerals of an ancient planet. Here beside us, it remains familiar and calm. Let the day soften like ripples fading on a dark sea, and rest with the quiet wonder that the simplest liquid you know may also be one of the universe's deepest clues. And now, my friend, we have reached the end of this quiet journey through water. We have seen that water is far more than a simple liquid. It is a molecule with a strange shape, a hidden network of bonds, a surface that behaves like a delicate skin, and a substance capable of shaping climates, landscapes, living cells, and perhaps even the search for life beyond Earth. So the next time you hear rain against a window, see ice floating in a glass, or watch a river moving slowly under the light, maybe it will feel a little different, a little deeper, a little more mysterious. If you're still awake and would like to keep drifting through science, you can choose another video and let the journey continue. Thank you for spending this time with me, my friend. Rest well, let the night be gentle, and sweet dreams among the stars.